PFAS are called forever chemicals because they're really difficult to break down. In fact, one of the primary uses of PFAS and why they're out in the environment in vast quantities is because they were used as firefighting foam. They were a principal compound in this foam that was used to put out jet fuel fires. That means they're really difficult to break down. We're actually doing it with, believe it or not, mechanical energy. So we're energetically grinding dirt, basically pulverizing it into smithereens, and that encourages the chemistry that breaks down PFAS. So instead of separating out PFAS from dirt or removing it, we're breaking it down while it's sitting there in the soil.
Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hardware to Save a Planet is brought to you by Synapse. Make sure to click subscribe so you don't miss any future episodes. Thanks for listening. Hello and welcome to Hardware to Save a Planet. Today I am thrilled to be here with Randol Aikin, the founder of Remedy Scientific. Randol and his team at Remedy are tackling the challenge of cleaning up land that has been contaminated by chemicals. We talk a lot about how human activity is warming the planet, but temperature change, of course, isn't the only impact, and this is a great example. I learned from this awesome explainer video on Remedy's website that there are about 500,000 contaminated sites just in the US. It's a $3 trillion problem and slows down development of housing, infrastructure, and industry. Current approaches for decontamination don't scale sufficiently to meet the challenge, which is where Remedy's solution comes in. They're using advanced sensing, robotics, and AI to accelerate the process to make this land usable again. To introduce Randol quickly, he has a PhD in physics from Caltech, where he did research on the origin of the universe. Throughout his career, he has worked on some very cool projects, including disaster relief, autonomous trucks at Uber and Ike, and residential energy storage with Lunar. Early in his career, he also spent 3 years at Apple as a senior technologist in the special projects group. And every time I see something like that, I get super curious about what that actually means. He founded Remedy a little over 2 years ago, but just came out of stealth in the last couple of months with a post on LinkedIn that caught my eye. Randol, it is great to have you here. Thanks for joining.
Thanks for having me. Great to be here.
Yeah, you were doing this for 2 years in stealth. You're out in the open talking about what you're doing. How does that feel?
The reason for being in stealth so long is because I think that this is going to be a category where there's a lot of competition, but we're kind of a weird company right now. We're, I think, an N of one, and we wanted to keep it that way for as long as possible. So it feels great to tell the story more publicly, get folks rowing in the same direction, get folks excited about what we're up to. So we're really excited to share, and the response from the community has been tremendous since coming out of stealth. So that's been really, really exciting.
Nice. Yeah. No, I was really excited to see what you're doing. Maybe just rewinding, I'd be curious kind of what led you here. So you've had this really sort of varied career. I was trying to kind of pick up on common threads. It seems like autonomy maybe is a common one, but you've had this sort of diverse set of experiences, it seems like.
Call it a non-linear career path.
Yeah, exactly.
I worked on a whole bunch of stuff, and I think that the thing that all of these have in common, whether it's autonomous trucks or autonomous cars or residential storage, virtual power plants, airborne surveillance, is that they're all systems problems. They're all hardware and software problems. Those are the kinds of problems that I tend to be attracted to, where it's not a software widget, it's not just a better mousetrap, it's actually hardware and software working together to do something really interesting. And I think that the other piece for me professionally is that impact is obviously key. Important is more interest is bigger than interesting. And so I think finding these outsized opportunities to move the needle in different categories is really important to me in my career.
Mm-hmm. What was it about decontamination of land that caught your eye? Like, how did you land on that as the next problem to tackle?
Gosh, it feels like there were a bunch of arrows all pointing in the same direction over the course of the last decade of my career. And in some ways, it's very much a backyard problem. I live in Oakland, and here in the Bay Area, we're just surrounded by contaminated sites. And you've probably experienced this too, where you drive by some premier piece of real estate and it's underdeveloped or it's just surrounded by a chain link fence. Why is there nothing here? And it turns out the answer is often environmental contamination. And so we're surrounded by it. It's one of these things when you start paying attention to it, you can't unsee it. It just shows up everywhere. But then, I think that this is also fundamentally getting back to this interest in land use. And in the early days of autonomy, when we were working on getting cars to drive themselves, the most interesting part of that technology at the time for me was about land use. It was about how are we going to convert parking lots into parks? How are we going to change road infrastructure in this country when autonomy is widely deployed? Like that's one of the most interesting parts of that technology. We haven't gotten there yet, but this interest around land use and using technology to change the built environment that we live in, and that we don't have to just live with the inherited decisions of people that came before us. That is what's compelling to me. That's what's interesting.
Okay. So all this contaminated land is you see as an opportunity to kind of rethink the way we're using this land that has been previously kind of dumped on, or how do you want to look at it?
Absolutely.
Yeah.
And I think in the context of climate, this is climate is a story about land use, right? And when we think about both the impacts of climate and the response to climate, we talk about energy generation and storage, and we talk about transportation. And gosh, like think about two categories that have had a bigger impact on land use in this country than those two. And it's like maybe agriculture, which also has its own giant climate story around it. And so there's just no version of a giant energy transition or a giant transportation transition that doesn't have to contend with land use. It's just a key part of this story. And core to that is environmental contamination. And how do we take industrial land and put it back to productive use instead of always resorting to greenfield development?
Hmm. Illustrate that a little more for me. Like, what are some examples of land that has been contaminated? How, what are common sources of this contamination, and what could we be doing with that land that we're not able to do today?
Yeah, it's a great question. The figure you cited earlier, by the way, 500,000 brownfields in the US, that's a number from the EPA that's over 20 years old. The number
Okay.
is much, much bigger than that, but the EPA hasn't
Wow.
produced a more recent number. So think about corner gas stations, think about former landfills. Uh, Actually, just a couple weeks ago, they announced the closure, Valero announced the closure of this huge refinery in Benicia here in the Bay Area. That's a 900-acre site. And I hope in my lifetime we are closing a lot of refineries. But what do we do with that land? How do we put it to productive use? Are we just going to live with that being a former refinery for the rest of our lives? We should be dissatisfied with the answers that we have today. And the opportunity for technology injection here is just tremendous. So this also gets to, I mean, think about how many gas stations are going to have to close if we're moving toward electrified vehicles. Like that's a huge, huge real estate opportunity, but you can only take advantage of that if you can manage the contaminants and the legacy of that historical land use.
Mm. And I guess why is that? Like, what has a gas station done to the land that's preventing development before it's decontaminated?
For gas stations in particular, the big issue is what they call leaky underground storage tanks. So at gas stations, you have an underground storage tank that they use to hold fuel. And it turns out that for many, many years, they weren't very good at monitoring those things for leaks. Modern storage tanks are much, much better, but there are all kinds of leaky storage tanks that are just scattered across the US. There's a whole EPA program just focused on that. And so there's a reason why it's really difficult to redevelop gas stations into a housing complex, for instance. And it's because there are these legacy contaminants in the ground that create entitlement issues. It creates permitting issues. It creates real remediation cost issues that prevent redevelopment. It impacts even weird things like former auto dealers. Most of those auto dealers had auto shops attached to them, and those auto shops could have all kinds of contaminants, solvents, heavy metals that end up in the ground. And so now, as part of a redevelopment, you have to contend with all of those contaminants in addition to permitting issues and vertical construction and all of the rest.
Mm.
So this is a major barrier. And for the worst sites, for the big Superfund sites that we have to contend with, the reality is that more often than not, the contaminants just stay in the ground, and we're just monitoring those sites to make sure that the broader impact to the community isn't too bad. But that's a really unsatisfying answer, right? We should be able to take these big industrial sites and put them back to productive use.
Hmm. And I guess by developing them, you're kind of exposing all those contaminants or risking their leaking into nearby environments and things like that is the reason
Yeah,
why they're sort of locked down from further development.
yeah, absolutely. And then there's also just a huge environmental liability that comes with owning those assets. And so it's in some cases, these sites sit on corporate books valued at $1 because the liability attached to those sites is so much more than the land value. And it's a huge issue. And the reality is, so if you take all of this together, what this means is that we are polluting land and contaminating land at a rate that far exceeds cleanup. And that's true of the United States. It's worse everywhere else, basically. And that puts us on a path to basically polluting ourselves off of the planet. And we just have to be able to repurpose contaminated land, especially at industrial sites, especially where heavy power is available. And that's something where environmental contamination just presents a huge barrier today.
It makes me think about this very sort of constant debate in the carbon removal space, or as related to CO2, where there's this debate about should we spend resources and time and money on taking CO2 out of the atmosphere that's already there, or on stopping future emissions or reducing future emissions. Um,
Yeah. Yeah,
uh,
there's
yeah,
I love
yeah.
that.
Go
There's
ahead.
there's absolutely a similar concept in this
Right.
world to net zero, where we need to get into a place where the rate at which we're putting contaminants into the ground, which is candidly unavoidable if you're doing manufacturing, if you're doing the kinds of industrial activities, especially that we want to onshore, but we need the ability to clean them up rapidly. And I think if you take a step way back and look at the state of environmental in the US, we've done a lot of really good work on the prevention side of this, of preventing and disincentivizing pollution and then penalizing those folks really, really heavily when it happens. And so the carbon analogy here is that we've gotten really good on the emission side. But on the direct air capture side, or pulling carbon out, dealing with historical remediation, we are so far behind and there's so
Mm,
much work to be done.
got it. So that's really the place to focus.
I think so. Yeah.
Hmm. What kind of contaminants are we talking about? Like, what are I saw you're focused on PFAS initially in your I think on your website. I read that. Is that is that sort of the biggest problem, or yeah, what are we actually talking about?
PFAS is the newest problem. It's not the
Okay.
biggest, in my opinion. PFAS is what they call an emerging contaminant, which means that new regulations are based on good science about the toxicity of this compound. I should say these compounds because there's many of them, is informing uh, both cleanup and new water standards. It's informing a whole bunch of work that has to happen in order for us to get those synthesized compounds out of our soil, out of our water systems, eventually out of our food systems. But that's, the tip of the iceberg, frankly.
Mm,
And there are inorganics. So think of things like lead and arsenic and chromium. There are volatiles. So think about oil spills. Uh, the list goes on and on and on. And it's unfortunately a list that is only ever going to grow as we understand the toxicity of pesticides and pharmaceuticals, for instance, that have made their way into our food systems. I believe that the list of regulated toxins in the environment is only ever going to get longer. I don't think that list is ever going to get shorter. And today, again, often the case when we have those types of environmental contaminants is that they stay in the environment and eventually make their way into our bodies. So
yeah. And there are solutions today to do this, or to do decontamination of some kind, right? You talk a bit in your materials about how you're improving on sort of the technology of today. Can you talk a little bit about what our options are in a world before Remedy comes along,
Yeah.
and then why what you're doing is an improvement on that.
Yeah, absolutely. I would say that we can talk about PFAS as a separate category, but if we look at the state of environmental remediation, it shares a lot in common with construction, where, for instance, there's a lot of incompressible costs in environmental remediation. So, dig and haul, where you're digging up contaminated material and then transporting it to a, a landfill and depositing it there, is a really common
Hmm.
remediation method, and that has a bunch of incompressible costs with it. Trucking is hard to make cheaper. Landfill tipping fees are hard to make cheaper. And so that's something that is hard to scale for that reason, but is still commonly done today. There are a bunch of really interesting, good treatment technologies for groundwater, for all types of different contaminants. And the same is true for soil. They tend to be labor intensive. Often they focus on binding or stabilizing a chemical or a compound in soil as opposed to destroying it and actually getting to the root of the problem. And
Hmm.
so I would say that generally the issue that we have today is that the technologies that we use for site remediation are not products. They're site specific projects. And so there will
Hmm.
be a specific solution that's designed for a site that's usually a pretty complex combination of dig and haul methods versus you may have some underground injection of some compound. You may bring a groundwater treatment system to that site. And this process of designing, deploying, commissioning, confirming this thing works takes years and years and years. And I come from a world of products, right, where we
Hmm.
build modular designs that can be used for a variety of purposes and can achieve different missions at different sites. And that's really, I think, the thing that's missing here is we want to be limited by the number of machines that we can build in terms of how much remediation we can do in the world, not by the number of people that we can hire and deploy to do this work. So,
So, what has been your angle? Like, what's your how have you made it possible to do this with a product based approach rather than today's approach?
yeah, this is a part of the reason that we focus on PFAS, but we've
Hmm.
developed a PFAS treatment for soil that packages into a 40-foot shipping container. And we haul that shipping container to a site. We deployed a couple weeks ago and we found it took about 2 hours to commission this system. And then we start processing dirt. And this process, frankly, is kind of a dumb process, meaning that it treats all different types of compounds related to PFAS, all kinds of different PFAS compounds. It's not specific to one type or flavor of PFAS. And so we can start treating PFAS the same day as we've deployed that system. And that gets rid of years of work of site specific design and
Hmm.
commissioning and all the things that typically go along with this sort of project based approach that's common in environmental remediation today.
Hmm.
So the idea is just for this specific example, you go to a site, you've mapped where your contaminants are, you excavate the contaminated dirt, and then instead of sending it off to some distant landfill, you put it through our machine. And then after it's gone through this machine, you can take the clean dirt and put it back into the ground.
Okay, and it's PFAS free.
And it's PFAS free.
Okay, just a probably a naive question, but they call these forever chemicals,
Yeah.
right? Like they're what are you actually doing to uh, destroy the PFAS or neutralize it? What's happening?
Yeah, it's not a naive question at all. It's really hard, right? So PFAS are called forever chemicals because they're really difficult to break down. And
Hmm.
in fact, one of the primary uses of PFAS and why they're out in the environment in vast quantities is because they were used as firefighting foam. So they were a principal compound in this foam that was used to put out jet fuel fires. And
Hmm.
that means that they're really, really difficult to break down. And so even incineration methods require, 1,000 degrees Celsius. Desorption requires 400 degrees Celsius, very, very high temperatures to deal with this stuff. Other folks use plasma, and they use supercritical water oxidation, these like highly intensive methods to break PFAS down. And ours is similar. We're actually doing it with, believe it or not, mechanical energy. So we're energetically grinding dirt basically pulverizing it into smithereens. And that actually encourages the chemistry that breaks down PFAS. So instead of separating out PFAS from dirt or removing it, we're breaking it down while it's sitting there in the soil. So that excavated material goes into this high energy ball milling reactor where we grind it, and that grinding actually enables the chemistry that allows PFAS to break down.
Cool. Is that an innovation that you're bringing to the table, or is that's a known
Absolutely
process?
not. No,
Okay.
this is something that's been around for 30 years. It actually
Got
began
it.
used in a different type of application for different types of
Yeah.
contaminants. The thing that I think is unique about what we've done is two things. One, we just ran thousands of experiments to optimize this process so that we could get something that works really, really well, both from an efficiency perspective, but then also is just really good at breaking down all different types of PFAS compounds. And then the other thing is that we basically made it possible to measure PFAS precisely in soil in the field. And the reason that that's so important is because you're turning an open loop system into a closed loop system. It means that you can put contaminated dirt in, you know the type of PFAS compounds that are in there, you can confirm on the way out that they're actually gone, and that allows you to tune the system in real time in this way that's never been done before. So I think that those are the two areas where we've done something new here. But the core science around this has been literally around for decades, based on some really, really good work by folks that came before us.
Yeah, I was gonna ask about like how you know where and how much PFAS is present. And it sounds like you have the actual sensing technology to support that.
Yeah, basically what we've done is we've taken a PFAS analytical lab and added robots and then put it in a small shipping container. So you can take a scoop of dirt, you run it through a bunch of robots, and it tells you how much PFAS is in it. So even the core sensing technology it's not net new. We're leveraging
Mm.
existing technology, but we're just in the same way that we did in the robotics world of trucking, we're taking a bunch of existing technology, integrating them together to accomplish something new. And
Yeah.
we've done this in sensing in a way that I think is totally unique in this world.
Yeah. What have been some of the technical challenges you've had to overcome to get to where you're at today?
That's a good question. I would say that probably the biggest technical challenge is that soil is really complicated. Our head of
Mm.
chemistry always uses the phrase, it's a dog's breakfast of chemistry. There are so many things going on. And so what that means is that when you do an experiment, often the results are really difficult to interpret because there are so many competing mechanisms that happen within soil because there's so much chemistry in soil. And I think that that has been one of the reasons that we've had to do so much work to both understand what's in the soil to begin with, to do all this analytical work up front, but then also conduct these thousands of experiments because it's such a huge parameter space to explore. And at the same time, the chemistry that's present in the soil is really complex. So I would say that that's probably been the biggest challenge today.
You talk about AI. Is that where your algorithms come in?
That's right. And here, AI is probably a little bit of an overused term. Really, what we're doing looks more like traditional machine learning. We're using
Got it.
fairly straightforward machine learning models just to pull out non obvious insights in this huge data set that we've assembled. And again, this is an area where there's been some work that's been done in this before, but there's also a lot of low hanging fruit. And this is not just true for environmental remediation, but I think in a lot of the things that I've worked on in my career, there's huge opportunity where you can cross pollinate technologies between different industries. And there are a lot of things that we've learned about insights, back end processing techniques, front end tools, all of these different things that are really common in the world of robotics today that we're
Hmm.
cross pollinating into the world of environmental remediation in this way that I think adds a lot of value. So in the world of AI and ML, what we're doing is candidly not earth shattering here, but by doing some pretty lightweight work and just also creating this massive data set that we can use for training is an easy way for us to find new insights about how this process works.
And where are you in the development process? It sounds like you have a system that you're deploying and using actively to remediate sites.
Yeah, we've built this pilot system. The hardware team has been really hard at work building this thing and getting it out into the field. And so getting out into the field last month was a really big milestone for us and for the team.
Nice,
We've
congrats.
scaled this process by a factor of 1,000 in the course of about 12 months, and we're going to continue to scale it. I think that one of the things that has been nice about this problem is that the continued scaling has not uncovered huge mysteries or huge challenges. And for
Mm,
a chemical process, that's often not the case, where as you scale some kind of synthesis process, often you have to contend with how do you tightly control the environmental variables? How do you tightly control contaminants so that it's not changing the conditions if you're trying to produce a new type of green plastic, for instance? And
mhm.
for us, we're dealing in dirt and we're actually destroying chemicals instead of making them. And so the scaling of this process has been comparatively straightforward. So
So you talk about scaling in terms of it sounds like you've scaled sort of the throughput of your process or
that's
the
right.
volume of dirt you can manage. As I understand it, you'll also eventually have to scale the number of machines you build, right? You'll
Yep.
have to sort of productize this and scale the manufacturing of these so you can deploy these to lots of different sites. Is that kind of the
Absolutely.
next big frontier for you?
That's right. But I think one of the things that we should also be encouraged by is that there's a lot of PFAS in the world, but the number of highly contaminated PFAS sites is actually fairly manageable. So,
Mm,
for instance, there are 580 DoD sites today that span Navy, Army, Air Force, where they have reason to believe that there's some amount of PFAS contamination at that site. And some of these, this is a matter of public record. Some of these sites are very, very contaminated. And there are, when we talk about water, we talk about parts per trillion as being the standard for the level of PFAS that's allowable in that water.
mhm.
At these sites, we measure parts per thousand. So
Oh,
these
wow.
are very, very contaminated sites, but we know where they are, and there aren't that many of them. So with a couple dozen of the machines that we're designing today, we can treat all of these. And that's our aim. Our aim is to be the best, the most obvious, the most effective PFAS treatment solution for these highly, highly contaminated sources of PFAS in the environment.
Interesting. So the sort of does that mean that the total addressable market is something is like this finite thing that you could go clean up and you're done at least with that with the PFAS problem at least the like the lowest hanging fruit PFAS
For
problem.
DoD, for PFAS, absolutely. That is
Yeah.
a capped addressable market, and we want to go
Hmm.
run the table on that market in like 5 years. Like we just should go clean up all of those sites, and that's
Mm-hmm.
very doable. The technology now exists to go do that, and I think that that also means that this is opinion now that we should be putting a lot more money toward cleanup and a lot less money toward investigation. And so, as an example, the federal government is going to spend 4 times as much on investigation as they are on cleanup for PFAS this year. And we just need to start cleaning up these sites. We know where they are. We now have the technology to clean it up. We just need to get to work. But when it comes outside of PFAS and we talk about environmental contaminants broadly, there's basically infinite supply of contaminated land assets. And so
Hmm.
I am not worried about market size at all.
Right. So you can take the same approach, same kind of fundamental productizing the process approach to other contaminants
You
and
got it.
have plenty of
So the
market to go
fundamental
tackle.
treatment technology is going to be totally different when we talk about lead or when we talk about arsenic or when we talk about VOCs. Totally different, but the approach is the same. It's taking something that today is a very manual, site specific solution and turning it into a product that's software defined that you can deploy in a day.
Hmm. So my next question was going to be about the business model. It sounds like it probably depends on the types of sites we're talking about. Some of these are government or DoD facilities, and then I imagine there's a big sort of private sector um, market once you get outside of that. What is the business model? Kind of who's paying for this? How do they justify that expense? That kind of thing.
Yeah, it's a great question. Basically, we think about three big sectors for our technology. The first is federal.
Hmm.
Federal is a big deal because by most measures, the federal government is the biggest polluter on the planet. That's not just in the U.S., that's across the
Hmm.
globe. So they're a big customer, and the goal is to make them not a big customer in the future. Right? That's something that we hope is not true in the future.
Hmm.
The second is waste, and so actually, big companies like Clean Harbors or Republic Services or Waste Management handle millions of tons of contaminated material over years. And so that's in part because they manage hazardous waste landfills. It's also because they get involved in cleanup projects and they do really, really good work. And so there's opportunities for us to help there. That's primarily on the sensing side. That's an important sector for us. And really sensing is an ability to become more focused in how we apply things like dig and haul. So we're not hauling 20,000 tons of dirt when we could haul 1,000 tons of dirt.
Hmm.
And that's just improving the amount of data, the data visibility at a site using our sensing technology. And then the third is private sector. And for private sector, that is a complex world that involves big companies that manage lots of small contaminated sites. It's also big companies that manage giant contaminated sites. And there are a lot of stakeholders in that world. But like I say, there's also a ton of supply. So to answer your question about what the business model looks like, it really depends on the sector. And so for
Hmm.
federal, I think it's really important that we're a good services provider for the federal government as a client. In the private sector, I think there are actually a number of ways in which we can provide this unique service and find different ways of capturing the value that's created from cleaning up contaminated land. And so I think that one of the things that we hope to do as a startup is change the dynamics of the business model of environmental remediation a little bit, where we're not just paid for efficacy, we're also paid for efficiency. So that means working on fixed price contracts instead of working on time and materials contracts. And then it also means that we're participating to some degree in the upside, the value creation of cleaning up otherwise useless land.
Hmm. Got it. You talked at the beginning about competition or the potential for competition. I mean, it does seem like a huge market the way you're characterizing it. Is there competition today, or is the potential competition mostly companies doing something very similar to what you're already often doing?
Competition is a funny thing in this world because in this industry, you always hope that more people are working on the problem and are seeking solutions
Hmm.
to complex environmental challenges. And so I think that look, there's so much good work that's happening in water related to PFAS.
Hmm.
I think it's safe to say that the primary focus of PFAS is water. The work that those companies are doing is so important and it's really, really high quality work. I think naturally soil has had less of a focus, even though soil is actually often the way in which PFAS ends up in the water in the first place. And so, just from a cost perspective, if you want to get rid of PFAS in the environment, go to the place where it's highly, highly concentrated, clean up the hotspot rather than waiting to clean it up in water. So, from that perspective, I think what we do is very much complementary to what folks are doing in PFAS in water, not in any way competing. I think in terms of the other parts of the business of building products, scalable products to address a wide variety of contaminants in the environment, I'm not frankly aware of anybody that's trying to tackle this problem in quite the same way. And I would love for there to be a whole new category of companies that are
Hmm.
trying to crack this nut. So
Yeah, makes sense. When you think about the future of the company, I mean, you described this as kind of infinite supply. Uh, can you quantify the kind of impact you believe you can have, or what the future of yeah, what the future scale of Remedy looks like?
like I say, even in the short term, let's talk about like the next 3 to 5 years. I
Hmm.
think a few dozen of these machines deployed out in the world and surfacing these DoD sites is going to make a substantial difference in how much PFAS is in the world 50 years from now. And it's because these hotspots are a ticking time bomb. They're just hugely, hugely important in terms of how much PFAS is going to disperse out into the environment in the decades and centuries to come. So we should be cleaning up those sites now. Other folks are working on this problem too. It's an important problem to solve. So from that perspective, even in the short term, with this first treatment technology that we've developed, there's huge opportunity for impact. I think longer term, I'm really excited about a future where an environmentally contaminated site just doesn't have to stay that way. And we can repurpose this vast, vast acreage of land across the US that today is just sitting there dormant. The contaminants are staying in the ground and eventually finding their way into our bodies. And instead,
Hmm.
you can haul machines onto that site that are going to clean up the contaminants, repurpose the land, put it back to productive use in months, not decades or centuries.
Hmm. It's actually like this very kind of refreshingly optimistic uh, story that with a small number of these machines, one of which you've already built, you can have such a big impact in a just a handful of years. That's pretty cool.
I think that is something that makes me really excited about this space. Another thing that makes me really excited about it is that when we're talking about clean energy transition or we're talking about electrification, there can often be this conversation about how do we trade off between speed of development and then protecting the environment and protecting human health. And so folks will talk about things like permitting reform is a really big part of how we deploy renewable energy quickly. And that's a really important conversation to have. I also think it's really important to think about technology as being a solution here, where technology is a way of breaking this false compromise between protecting the environment, protecting human health, and developing at speed. So I think
Mm,
that's another reason here to be really optimistic about the future is that there are actual real opportunities to do better here where we don't have to live with this false choice that we have to live with today.
yeah, I love that. It's actually a good segue to my last few questions, which I'm ready to move on to, unless there's anything we didn't hit that you were hoping to talk about.
No, that's great.
Okay. So I have three questions I ask everybody, and the first is yeah, a good follow on from that chat. How optimistic or pessimistic are you about the future of the planet, and why?
That is a tough question. The thing I usually say is that the more optimistic I get about our business, the more depressed I get about the state of the world. But I I think that there are always reasons to be optimistic. And I've got a 7-month-old daughter at home, and I think there's basically never been a better time to be alive than now. And think that's going to continue to be true in the future. Doesn't mean that we have big, big problems to solve, but if you take a step back, it's a really, really good time to be alive.
Who's another company or individual doing something to address climate change that's inspiring you?
That is a very interesting question.
I'm sorry, I don't think we prepped you with these before, so take your time.
Um, Give me 2 seconds. Let me make sure that I get the name right. Yeah. Okay. I'm a really big fan of Block Power. Block Power is this
Mm,
really interesting company that's focused a lot on HVAC in highly inefficient homes. I think
mhm,
it's a really interesting example of how do we apply straightforward technologies, integrate them into existing infrastructure in a way that really moves the needle on efficiency and energy consumption. I think that we tend to underemphasize those types of opportunities. And I think Block Power is a really good example of doing that well.
mhm. Yeah, love those guys. I think they're doing a lot of work in New York City, right?
That's right. Yeah.
Yeah. What advice do you have for someone not working in climate today who wants to do something to help?
I would say that probably the most important thing is be aware of the tools that are at your disposal. So in my world, I work in the world of startup. And that means that for us to have impact, we need to scale. It also means that our business objectives need to be precisely aligned to the mission that we're trying to accomplish. So in the short term, what that means for us is that we need to process as much dirt as we possibly can. And that both reflects the impact and it also reflects the business opportunity. But startups are not the only way to have impact, and maybe not even the most important way to have impact in climate. And so if you're in academia, growth is not the objective. Revenue is not the objective. If you're at a big company, that may be true as well. So I would say that the most important thing is you make sure that you're leveraging the tools that are available to you.
Nice. Randol, that was really fun. Love what you're doing. Thank you so much for your time.
Yeah, thanks for having me. It was really fun.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.